Hi, welcome to Sunil Maths tutorial. Galois theory, class number 9. In the first unit, this is third topic, algebraic extensions. First definition is algebraic. Let us see the first definition, algebraic. This topic name is algebraic extensions, but the first definition is algebraic. So right, let us take capital E is an extension of capital F. So capital E is an extension field of capital F. An element alpha belongs to E. An element alpha belongs to the extension field capital E that may be lies in F or may not be lies in capital F is said to be algebraic over the field capital F if there exists some constants a0, a1, a2, and so on an. Remember that not all 0, such that they satisfies one condition, a0 plus a1 alpha plus a2 alpha square plus and so on plus an alpha power n is equals to 0. Then we say that the element alpha belongs to capital E is algebraic over capital F. Is algebraic over capital F. That's it. So remember that here capital E is extension field. Capital E is extension of capital F. It means F is subset to E. And the element alpha belongs to E. And the element alpha belongs to E is said to be algebraic over capital F if there exists a0, a1, a2 and so on an. They belongs to the field capital F. They belongs to the field capital F. But remember that they are not all 0 such that they satisfies this condition. The same definition algebraic in another words. An element alpha belongs to capital E is algebraic over capital F if there exists a non-constant polynomial p of x that belongs to polynomial ring capital F of x such that it satisfies the condition p of alpha is equals to 0. It means the element alpha belongs to E becomes a root for the polynomial p of x which lies in the polynomial ring f of x. So that's it. After this definition, we prove a theorem. Let us see that. Let us capital E be an extension field of capital F and U belongs to capital E be the algebraic element over capital F and P of x belongs to capital F of x be a polynomial of least degree such that P of U is equals to 0. Then there are three conditions. First condition, P of x is irreducible over capital F. Second one, if G of x belongs to capital F of x such that G of U is equals to 0, then P of x divides G of x. And third condition, there is exactly one monic polynomial P of x belongs to capital F of x of least degree such that P of U is equals to 0. So we prove this step by step. So there are three properties. We prove this step by step. Let us see. Capital E is extension field of capital F. Capital E is extension field of capital F. And there is an element U belongs to capital E is algebraic over capital F. U is algebraic over capital F. Then by the definition of algebraic, there exists a non-constant polynomial f of x that belongs to capital F of x such that it satisfies the condition f of alpha is equals to 0. Instead of f of alpha is equals to 0, here we are using that element alpha, we are using the element u, so f of u is equals to 0. I repeat it, E is an extension of F and U belongs to E is algebraic over capital F. By definition of algebraic, there exists a non-constant polynomial f of x in capital F of x satisfying the condition f of u is equals to 0. Also they given that p of x, also they given that p of x belongs to capital F of x be a polynomial of least degree, smallest degree, least means of smallest degree, such that p of u is equals to 0. Now our aim is to show that p of x is irreducible. That is the first case. Our aim is to prove that p of x is irreducible over capital F. If possible, assume that p of x is reducible over capital F. What is mean by reducible? This p of x can be written as product of two non-constant polynomials f1 of x into f2 of x. Let it be equation number 1. Actually, we are going to prove that it is irreducible. We assume the contradictive point p of x is reducible. By the definition of reducibility, p of x can be written as product of two non-constant polynomials. P of x is equals to f1 of x into f2 of x. If p of x is equals to f1 of x into f2 of x, here this is from this equation 1, f1 of x into f2 of x is equals to p of x means where degree of f1 of x and degree of f2 of x both are less than degree of g of x. I mean the degree of the factors f1 of x and f2 of x both are less than the degree of p of x. Now replace x by u in this equation 1. Replace x by u in equation 1. What you get? P of u is equals to f1 of u into f2 of u. By data p of u is equals to 0, it means 0 is equals to f1 of u into f2 of u, which means either f1 of u is equals to 0 or f2 of u is equals to 0, which means f1 of u is equals to 0 means u is a root of a polynomial, f1 of x, such that its degree, degree of f1 of x is less than degree of p of x. But actually what is the truth? P of x be the polynomial of least degree such that p of u is equals to 0. But we get one more polynomial f1 of x and such that f1 of u is equals to 0, and degree of f1 of x is less than degree of p of x. This is a contradiction. To the given fact p of x is the smallest degree. P of x is the polynomial having smallest degree such that p of u is equals to 0. This contradiction exists because of our assumption p of x is reducible over capital F. Therefore, our assumption is wrong. Hence, our assumption p of x is reducible is wrong. Therefore, p of x is the irreducible polynomial over capital F. This is the first point. Next, you have to show that the second point. Our aim is to prove that if g of x belongs to capital F of x such that g of u is equals to 0, then p of x divides g of x. Yes. Here you observe that the polynomial g of x belongs to f of x. Already we have a polynomial p of x that also belongs to capital F of x. We know that the polynomial ring capital F of x satisfies division algorithm. Now we have two polynomials. One is g of x, one is g of x. The second one is p of x. Both are belongs to f of x. Both are belongs to f of x. And every polynomial ring satisfies the division algorithm. By applying division algorithm here, there exists two another polynomials q of x and r of x in the same polynomial ring capital F of x, such that g of x is equals to p of x into q of x plus r of x, where either r of x is equals to 0 or degree of r of x is less than degree of g of x. I just write the division algorithm. The ring of polynomials f of x satisfies the division algorithm. Then there must be two polynomials q of x and r of x in capital F of x satisfying this condition g of x is equals to p of x into q of x plus r of x, where either r of x is equals to 0 or degree of r of x is less than degree of g of x. Okay, now suppose let us take in this equation x is replaced by u. X is replaced by u. So you get g of u is equals to p of u, q of u plus r of u. You get g of u is equals to p of u plus r of u. What it means? Already in the data we have, you see here, g of u is equals to 0. So you get simply 0 here. P of u also 0 into q of u plus r of u. So this condition implies as 0 is equals to r of u. It means u satisfies a polynomial r of x which belongs to capital F of x, which belongs to capital R of x. You clearly observe that degree of r of x is less than degree of g of x. This is not degree of g of x, I'm sorry, degree of p of x. Here also in the division algorithm also it is degree of p of x. Again this is a contradiction. Why? Because p of x is the polynomial of least degree. P of x is the polynomial of least degree such that p of u is equals to 0. But we get r of u is equals to 0 and degree of r of x is less than degree of p of x. So this is a contradiction. So to reduce this contradiction, it is very clearly r of x is equals to 0. It means this is a zero polynomial. R of x is a zero polynomial. If r of x is a zero polynomial, then from this equation what you get? If r of x is a zero polynomial, from this expression what you get? G of x is equals to p of x into q of x. Very clearly it becomes g of x is equals to p of x into q of x plus r of x, where this r of x is a zero polynomial. It means if it becomes 0, then g of x is equals to p of x into q of x. This condition shows as p of x divides g of x. That is the required second condition. You see here, if g of x belongs to f of x such that g of u is equals to 0, then p of x divides g of x. So second condition also completed. Next, you have to show the third condition. What is that third condition? We have to prove that there is exactly one monic polynomial p of x belongs to capital F of x of least degree such that p of u is equals to 0. Here we repeat the definition of monic. A polynomial is monic if the coefficient of highest degree is 1. Any polynomial is said to be monic polynomial if the leading coefficient an is equals to 1. Here also the polynomial p of x is a monic polynomial of least degree such that p of u is equals to 0. Actually our aim is to show that there is only one polynomial with this property. So suppose let us, there is another monic polynomial q of x belongs to capital F of x such that q of u is equals to 0. We assume that there is another polynomial with the same property as p of x. So by previous case, I mean case number 2, then there exists a polynomial, then p of x divides q of x and as well as q of x divides p of x. Combining these two conditions, what you get? P of x is equals to q of x. With the same properties, if there is another polynomial exists and we apply the second condition of our theorem, we apply the second condition of our theorem. If there is another polynomial, then obviously that polynomial p of x divides g of x. Then both we get p of x divides, here we assume that q of x is another polynomial, q of x, and same q of x divides p of x. So combining these two, we get p of x is equals to q of x. It means there is only unique polynomial. There is exactly one monic polynomial. P of x belongs to capital F of x of smallest degree such that p of u is equals to 0. This completes the proof of the theorem. In the next video, we learn about minimal polynomial. We learn algebraic extension. We learn some another theorem also. Keep learning. Wish you all the best.